Hey everyone, I hope you are doing great today. Today we will be going through the basics of glycolysis. I will do my best to explain as clearly as possible, and do leave any comments down below if you are unsure of anything or would like to clarify anything at all. Let us begin the journey of exploring the world of glycolysis and see how the entire process comes together. So what essentially is glycolysis? Basically, the word glycolysis can be split into glyco and lysis. Glyco means glucose and lysis means breakdown. So essentially, glycolysis is referring to glucose breakdown in our body. So how do we get glucose in our bodies? Well, of course, from the food that we eat. As we are all aware, there are three main macronutrients that we all take in: protein, carbohydrates, and fats. Carbohydrates are our main source of glucose because carbohydrates are broken down by enzymes to form your monosaccharides like fructose, galactose, and glucose, which are absorbed by your cells in various organs around your body for their energy purposes. As we can see on the left, I have added in the structure of glucose, C6H12O6. As indicated by the red numbers, we can count that glucose has 6 carbon atoms. This is especially important for later, where we see why soon enough. So where does glycolysis occur in the cell? Well, the cytoplasm contains the necessary enzymes and conditions required for glycolysis to occur. So here are the 10 steps of glycolysis, and I hope that you will be able to get a clearer picture and why each step is done. Alright, for step 1, what happens? As glucose enters the cell, we need to trap it and prevent glucose from leaving the cell. If not, it will be redundant and we are unable to use it for energy, right? So how do we do that? Well, simply, we add a charge to it to prevent it from leaving. So what happens is that in step 1, we will need this enzyme known as hexokinase to add a phosphate group to glucose. Note that hexokinase is present in all cell types except liver cells. In liver cells, glucokinase is present instead of hexokinase. So in liver cells, hexokinase is absent and glucokinase is present. So a simple search on Google and Wikipedia shows that a kinase is an enzyme that catalyzes the transfer of phosphate groups from high energy phosphate donating molecules to specific substrates. So in this situation, where do we get our phosphate groups? Well, I'm pretty sure you know this molecule called ATP, known by many as the energy currency of the cell. So what this does is that ATP donates a phosphate group to glucose at the 6th carbon. One way to remember this is that hex means 6. So it is a good reminder that the phosphate group is added on the 6th carbon. And this is the reason why the product is known as glucose 6-phosphate. Now, the production of glucose 6-phosphate will inhibit hexokinase. So this sign right here means that glucose 6-phosphate inhibits hexokinase. This means that this prevents more glucose from being converted to glucose 6-phosphate. Now, why is this so? This prevents excessive wastage of resources, as high concentrations of glucose 6-phosphate signals that the cell no longer requires glucose for energy for storage in the form of glycogen or as a source of biosynthetic precursors, and the glucose will be left in the blood. However, glucokinase is not inhibited by glucose 6-phosphate. Well, the lack of feedback inhibition by glucose 6-phosphate can be rationalized pretty easily. The liver's role is to regulate blood glucose. If blood glucose is too high, the liver must be able to take up glucose non-stop until the levels come down to normal. On the other hand, other tissues will stop taking up glucose when they have met their needs for it. So this is the structure of ATP for you, and as you can see, the phosphate group highlighted here in this blue box over here, will be transferred to glucose by enzyme hexokinase to form glucose 6-phosphate. So you can imagine it to be something like this. We have glucose over here, and then with the help of hexokinase, this will be added to glucose to form glucose 6-phosphate. Yes, indeed. So essentially, it looks just like this. So you might be asking, where's my memory tips? Well, for this first step, we have already discussed, and that the first thing that we will need for glucose is to trap it in, right? And now we do that with the help of hexokinase in all the cell types except for liver, while glucokinase does this instead in liver cells specifically. To remember what's the enzyme, remember that glucose has 6 carbon atoms. And 6 means hex. And this is why I said earlier that glucose has 6 carbon atoms, because it can give you a hint or a reminder about the name of the first enzyme involved in the glycolytic process. And to remember what is the product name, remember that hex means 6, and 6 is where the phosphate group attaches to the carbon. And where do we get our phosphate group from? ATP. Yep, that is right. That's why ATP is needed for this reaction. How do we transfer the phosphate group? Using a kinase. Yep, and a kinase is an enzyme that catalyzes the transfer of phosphate groups from high energy phosphate donating molecules to specific substrate. And we know that this reaction is irreversible, because if not, glucose 6-phosphate can be easily converted back to glucose, and this trapping step will be redundant if that indeed happens. And so that is the first step of glycolysis. Now, moving on, let us take a look at the second step. As you can see here, glucose 6-phosphate is converted to fructose 6-phosphate by this enzyme known as phosphoglucose isomerase. You can see that the COO double bond in glucose 6-phosphate over here, located on carbon 1, is shifted to carbon 2 in fructose 6-phosphate. So essentially, they have swapped places. Now, why is this necessary and significant? This is because fructose 6-phosphate has a structure that is more favorable for reactions. We will see why in step 3. In summary, Phosphoglucose isomerase catalyzes the reversible isomerization of glucose 6-phosphate to fructose 6-phosphate. So you must be asking, why is it called fructose 6-phosphate? Well, here is a photo of glucose. Notice this. And notice this, yeah? Yep. So and let's take a look at fructose. Oh, notice this. And notice this. Glucose, fructose, glucose, fructose, glucose, fructose. Oops. Oh, yeah. Anyways, you can see here that essentially in the process of converting the COO to carbon 2, the structure of glucose has become one of fructose. So now we can see why the product is called fructose 6-phosphate. This is because by swapping the COO of carbon 1 to carbon 2 in glucose 6-phosphate at the left here, now the structure is similar to that of fructose. Isn't that lovely? And since that has a phosphate group at the 6th carbon, it is called fructose 6-phosphate. Essentially, whatever here is what I've covered in the last few slides. We can see that glucose 6-phosphate is converted to fructose 6-phosphate by which enzyme again? Phosphoglucose isomerase. How can we remember that? A reactant is glucose 6-phosphate, which means that the name phosphoglucose makes sense. So we have seen what happens during step 2. But here is truly the beautiful part. Why is step 2 necessary? Well, let's find out in step 3. In step 3, fructose 6-phosphate is converted by phosphofructokinase to form fructose 1,6-bisphosphate. Which carbon does phosphofructokinase add to though? Well, it adds to carbon 1. Why carbon 1? Because it is in a favorable position where the OH functional group of the carbon 1 in fructose 6-phosphate is able to accept the phosphate group. Now it suddenly becomes clear and it all makes sense, right? Why we need step 2. Simply put, we need step 2 so as to prepare it for step 3 by making sure that the OH group is attached to the first carbon so that phosphofructokinase 1 can add a phosphate group to it. And of course, y'all will know the drill when we ask where do we get the phosphate group from. This phosphate group is from ATP, and this is exactly the reason why ATP is required for this step as well. This reaction is irreversible as well, and by now, this is the committed entry point of glycolysis, meaning that glycolysis will go through for this fructose 1,6-bisphosphate molecule. This 1 in phosphofructokinase 1 is important. How do we remember that? One way to remember is that it adds a phosphate group to the 1 in fructose 6-phosphate, forming fructose 1,6-bisphosphate. The name itself is pretty self-explanatory. Bisphosphate simply means 2 phosphate groups because bi means 2, just like how tri means 3. Are you still with me? Well, it only gets more complex, but interesting at the same time. In the next step, fructose 1,6-bisphosphate is cleaved by aldolase. The beautiful thing about aldolase is that it cleaves right smack in the middle of fructose 1,6-bisphosphate to form 2 products. One of them is called dihydroxyacetone phosphate, or DAP, at the top here,
And the second product is called glyceraldehyde 3-phosphate, or GAP for short. Note that these are formed in a 1:1 ratio. However, do note that only glyceraldehyde 3-phosphate is utilized for further reactions of the glycolysis process. So does that mean that dihydroxyacetone phosphate, or DAP, is rendered useless? Well, not exactly. DAP can be converted to glyceraldehyde 3-phosphate with the help of this enzyme known as triose phosphate isomerase. For those who are unsure, a triose is a monosaccharide or a simple sugar containing 3 carbon atoms. Now, the name of the enzyme makes sense. Triose phosphate isomerase means that the reactant DAP is a triose containing a phosphate group and will be isomerized to form a glyceraldehyde 3-phosphate. From here, we know what DAP stands for: dihydroxyacetone phosphate. For those who are interested and want to know how this name came about, I've placed an image of the chemical structure of acetone here for your reference. So in essence, from one molecule of fructose 1,6-bisphosphate, we are able to get 2 molecules of glyceraldehyde 3-phosphate. To remember what enzymes are involved, let's take a look firstly at the cleavage reaction. The enzyme involved is aldolase, which might be quite hard to remember because this is quite a specific and unique name, unlike the rest of the enzymes that we have come across thus far. So how can we aid ourselves in memorizing this? Have you heard of the shoe brand name called Aldo? So Aldo sells shoes, right? And what do shoes have? Shoe laces. That's right. Hinting when I'm going at Aldo lace, Aldo lace, Aldo lace. What a running joke, right? And another point. How do shoes come in? They come in as a pair, and a pair means 2, and 2 products are produced by aldolase. Now we are halfway there and there's 5 more steps to go. Now in step 6, we move on to oxidation of glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate is oxidized by glyceraldehyde 3-phosphate dehydrogenase, or GAPDH, to form 1,3-bisphosphate glycerate. The aldehyde groups of the triose sugars in GAP are oxidized and inorganic phosphate is added to them, forming 1,3-bisphosphate glycerate. This step is necessary because it helps with the generation of reducing equivalents NADH from NAD+, and GAP gains a phosphate group to the first carbon. Note that at the carbon 1 of 1,3-bisphosphate glycerate, the bond between the carbon and the phosphate group is labeled as a high energy bond. What does it mean? It means that this bond is unstable. And why is that significant? So with a high energy bond that makes the molecule unstable, it will want to get rid of it, right? And that is where phosphoglycerate kinase comes in the next step here. 1,3-bisphosphate glycerate is converted by phosphoglycerate kinase to 3-phosphoglycerate. During this process, the phosphate group which causes 1,3-bisphosphate glycerate to have a high energy bond and its instability is transferred to ADP to form ATP, and this makes the product 3-phosphoglycerate more stable. This type of phosphorylation, which involves the direct synthesis of ATP from ADP and a reactive intermediate, typically a high energy phosphate containing molecule, which is 1,3-bisphosphate glycerate. In this case, it's known as substrate level phosphorylation. We can see that in 3-phosphoglycerate, there is still a phosphate group attached at carbon 3. Now, our cells are very smart indeed. Once 3-phosphoglycerate is formed, it notices that it still has a phosphate group in it. So what does it do? Well, there is this enzyme called phosphoglycerate mutase that is present in the cell. What this enzyme essentially does is that it transfers the phosphate group from carbon 3 to carbon 2. And why is this necessary? Any guesses? Well, this is to simply prepare 2-phosphoglycerate, which is the end product of step 8, to form a high energy intermediate and to subsequently, you guessed it, proceed on with substrate level phosphorylation. In step 9, 2-phosphoglycerate is converted by this enzyme called enolase to form phosphoenolpyruvate. Water is produced as a side product because one hydrogen atom and an OH group is removed from 2-phosphoglycerate to form water, ultimately resulting in a C-C double bond between carbons 2 and 3. How do we remember the name of this product? Because our enzyme involved in this step is called enolase, you can guess that the word enol will be in there. And because substrate level phosphorylation still hasn't occurred, a phosphate group will still be present in the molecule. That's how you get phosphoenol, and by thinking that this is the last step of glycolysis where the end product is pyruvate, you can guess that the product of the 9th step of glycolysis is phosphoenolpyruvate. This generates a high energy bond between carbon 2 and the phosphate group, making it unstable. And at this point, you can already guess what is going to happen next. Of course, we are going to milk out the last phosphate group for phosphoenolpyruvate and generate ATP. So for step 10, where we generate our second ATP molecule, phosphoenolpyruvate is converted by pyruvate kinase to form pyruvate. In this process, our unstable phosphoenolpyruvate, due to the high energy bond, transfers the phosphate group with the help of pyruvate kinase to ADP, forming ATP and pyruvate, which is more stable compared to phosphoenolpyruvate. Therefore, it can be said that substrate level phosphorylation has occurred again. And that's all, folks. That's the 10 steps of glycolysis broken down for you. Let's do a short recap. So when we take in glucose, we first need to trap it by adding a phosphate group taken from ATP, and this is done with the help of hexokinase. Hex means 6, giving us a hint that the phosphate group is added at a 6th carbon. Next, glucose 6-phosphate is converted to fructose 6-phosphate with the help of phosphoglucose isomerase, because we want to convert glucose 6-phosphate into a form that we can add a phosphate group to. In doing so, the glucose structure has now become similar to that of fructose, and therefore we call it fructose 6-phosphate. Next, we add the phosphate group with the help of phosphofructokinase 1, again with the enzyme name giving us a hint that the phosphate group should be added to carbon 1, forming fructose 1,6-bisphosphate. Fructose 1,6-bisphosphate is cleaved by a wonderful enzyme known as aldolase to form two products, dihydroxyacetone phosphate (DAP) and glyceraldehyde 3-phosphate in a 1:1 ratio. DAP is not utilized in glycolysis, and so to convert it into a more useful product, glyceraldehyde 3-phosphate, triose phosphate isomerase is used in this conversion process. Therefore, from one glucose molecule, we can ultimately get two glyceraldehyde 3-phosphate molecules. Glyceraldehyde 3-phosphate is oxidized by GAPDH to generate reducing equivalent NADH, and in the process, a phosphate group is added to form 1,3-bisphosphate glycerate. Now, this 1,3-bisphosphate glycerate is an unstable molecule due to a high energy bond. Therefore, the transfer of this phosphate group relieves the unstable status of 1,3-bisphosphate glycerate, and the phosphate group is transferred to ADP to form ATP. This process of forming ATP from ADP and a phosphorylated intermediate rather than ADP and an inorganic phosphate is known as substrate level phosphorylation. Next, we prepare 3-phosphoglycerate for further substrate level phosphorylation by first shifting the phosphate group from carbon 3 to carbon 2, and we form 2-phosphoglycerate. This allows enolase to remove a hydrogen and a OH group to form water as a side product and generating a CC double bond. This forms a high energy bond between carbon and the phosphate group, rendering it unstable. And because phosphoenolpyruvate is unstable, it readily wants to attain the stable state. Therefore, with the help of pyruvate kinase to transfer the phosphate group from phosphoenolpyruvate to ADP, which forms ATP, pyruvate is generated as the end molecule, and ATP is generated through substrate level phosphorylation. What do we get out of one cycle of glycolysis? At the start, we used 2 ATP, and later on, from each glyceraldehyde 3-phosphate, we get out 1 NADH, 2 ATP, and 1 pyruvate. But remember that we are able to get 2 units of glyceraldehyde 3-phosphate due to the conversion of dihydroxyacetone phosphate to glyceraldehyde 3-phosphate by triose phosphate isomerase. So essentially, per glucose molecule, we can get an overall yield of 2 ATP, 2 NADH, and 2 pyruvate. So why 2 ATP? Because we get 4 ATP generated in the total from 2 GAP molecules, but minus the 2 ATP that we have invested at the start. You might be thinking, so we go through all that trouble just for 2 ATP? You can't be serious, that's totally not worth it at all. Well, there is more than meets the eye. What about the other simple sugars like fructose and galactose? How can we generate more ATP from pyruvate? In other words, what happens to pyruvate? Well, let me tell you this story another time. Do like and subscribe if you have learned more about the process of glycolysis, and do leave any questions or feedback down in the comments below. And I will see you next time. Take care and see you soon.